That's a good way to begin the day. All right, so we're going to continue with three-dimensional figures, and we're going to talk about some formulas that are associated with them. So a polyhedron is essentially a three-dimensional figure that's made of polygons. So a polyhedron is, most of the ones we talked about yesterday, prisms and pyramids, are polyhedrons because all the faces are polygons. However, a sphere, a cone, and a cylinder are not polyhedrons because what's different about these shapes?
They're round.
They're rounded. They don't have edges, right? So those are not polyhedrons. Polyhedrons are made up of edges, vertices, bases, and faces, whereas these not polyhedrons, so spheres, cones, and cylinders, have rounded edges. So they don't really have edges in the same way that a polyhedron does. So again, a polyhedron is made up of polygons, and not polyhedrons are not made up of polygons. When something is a polyhedron, you can use Euler's formula to prove that it's a polyhedron. So we use the vertices, the edges, and the faces to verify that it's a polyhedron. So vertices is V, edges is E, and F is faces. In any polyhedron, if you take the vertices minus the edges plus the number of faces, it will equal 2. If it equals 2, then it means it's a polyhedron. So this right here is a rectangular prism. How many vertices does this have? It has 8 vertices. Vertices are the what?
The corners.
Like the corners, yeah. So there's 1 vertex, 2, 3, 4, 5, 6, 7, 8 vertices. How many edges does it have?
11.
Almost. So there's 4 here, right? And 4 here. And then how many connecting them?
4.
So altogether it would be 12. And then how many faces does it have? 6, because it has the 4 sides and then the 2 ends. So then verify that this works. What's vertices minus edges? So 8 minus 12 would be negative 4. Plus 6 equals 2. So is that a polyhedron? Yes, because Euler's formula works, okay? So Euler's formula, V minus E plus F equals 2, can verify that they are polyhedrons. So if you take all the vertices minus the edges plus the faces, it will always give you 2. All right, so in this figure A, first of all, what is A? Is it a prism or a pyramid? Pyramid, what's the difference? Prism has 2 bases, and a pyramid just has 1 base, and then it goes to a common vertex up at the top. How can you tell what kind of pyramid it is? Whatever the shape of the base is, right? So the base here is a triangle, so this is a triangular. How many vertices does it have? 4. How many edges does it have?
6.
It has 6 edges, and how many faces does it have? 4. So then let's verify using Euler's formula for 4 minus 6 plus 4 equals, what's 4 minus 6? Plus 4? Good. Did that work? So is it a polyhedron? Yes.
Wait, so it's always going to equal?
It will always equal 2. V minus E plus F will always equal 2.
Why can't you just assume that's
Well, that sums up geometry. You can never assume.
So they're not curved or rounded.
They appear not to be curved. Is that a perfectly straight line?
Yes.
No, right? If you zoomed all the way in, you'd see what's happening here. It kind of curves down at the end, right? So you just can't assume in geometry. Pictures are never enough. You gotta prove it. You can't just assume it. All right, is this a pyramid or a prism?
Prism.
It's a prism. What kind of prism?
What's that? Pentagonal prism.
Pentagonal prism. What a nice return. Look at you. Wasn't even here. Pentagonal prism. All right, so how many vertices? How many vertices are there on the base? There's 5 here and 5 here, so altogether, how many edges?
15.
15. And how many faces? 7. Good. Okay. 10 minus 5 plus 7. 10 minus 5 is, 10 minus 15. Negative 5 plus 7. 2. So did Euler's formula work? So is it a polyhedron?
Yeah.
Yes. Could you assume that? Yeah, probably. Do you need to know Euler's formula to prove it? Yes. Okay. All right. The big thing is being able to name it and being able to tell the difference between a prism and a pyramid. All right, because ultimately what we're going to do is figure out the surface area and the volume, and to do that you have to be able to identify these. Okay. So again, like we said before, the difference between a pyramid and a prism has 2 bases, a pyramid has 1. So that means if I take a cross section is like doing what?
Cutting it in half.
Cutting it in pieces, right? However many pieces. What's the difference between the cross section of a prism and the cross section of a pyramid?
The prism would stay the same.
Yeah, the prism is going to be like every slice would look exactly like the base, whereas with a pyramid, every slice would be smaller, 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 or larger depending on which side you're cutting from. Good. Okay. All right, so we talked about with rhombuses and kites, we talked about diagonals. What's a diagonal? What's a diagonal? It's a slanted line. Where does it, let's say like if I'm talking about a rhombus, where does the diagonal go from? Corner to corner, non-consecutive vertices, right? So from one corner across the shape to the other. 3-dimensional figures all have diagonals as well. So in this rectangular prism, D is a diagonal because it goes from non-consecutive vertex to another non-consecutive vertex across the shape. Okay? All right, now, if we want to figure out that diagonal goes from here to here. What does X do?
Same.
X is a diagonal of what? Because X is a diagonal, but does it go through the whole shape or does it just go across the base? So X is the diagonal of the base. And what's H? The height. What shape does this make? Pretend that was a straight line. Yes, a triangle. What kind of triangle? A right triangle. So when you're looking for missing legs of right triangles, what theorem do we use? The Pythagorean theorem. So we can figure out the diagonal of any prism by using a variation on the Pythagorean theorem. So the first thing you would have to figure out is how long X is. So X also is part of a right triangle. What right triangle is that part of? This one down here at the base, right? So if X is the hypotenuse of this one, what are the legs of this right triangle?
The length and
X, W, and L, right? So L is a leg, W is a leg, and then X is the hypotenuse. Whereas in this triangle, which ones are the legs and which ones are the hypotenuse?
Would X be the leg?
X is a leg,
And D is the hypotenuse.
D is the hypotenuse, and H is a leg. Okay, so we're going to basically do the Pythagorean theorem, but twice to figure out what it is. However, we don't have to do that. We don't have to do it as 2 separate problems. You can essentially just combine the Pythagorean theorem twice in one problem. So to find the length of a diagonal, you square the length plus the width squared plus the height squared. So essentially what you're doing is length and width to find X, and then using that and H squared to find D squared. So again, you're basically doing the Pythagorean theorem twice, but instead of doing it in 2 separate steps, we just use this one formula to find the diagonal. So to find the diagonal of any prism, of any rectangular prism, we can use this formula. Length squared plus width squared plus height squared equals diagonal squared. Another way of writing that is like this. What's the difference between how I wrote it up here and how it's written down here? Yeah, we just square rooted the whole thing here, which does what to the D? It already square rooted it, so that no longer is D squared. Okay? So we can use that to find any type of missing piece that we're looking for. So let's say, for example, find the length of the diagonal of a 3-inch by 4-inch by 5-inch rectangular prism. So what's 3 inches, 4 inches, and 5 inches? That would be the length, width, and height. Does it matter which is which? Not really. All right, it doesn't matter which is which. So we're going to use the formula, which is L squared plus width squared plus height squared, and take the square root of that whole thing. So how would I start? What's 3 squared? 4 squared? And 5 squared. All right, what's 9 plus 16? 25. And what's 25 plus 25? So D equals square root of 50, which is a little over 7. The square root of 49 is 7. Okay? You can leave it like that. You can simplify it into a decimal if you'd like. I don't care. It'll be like approximately 7.03 probably. Something like that. What would be different about number 2? Yeah, we're looking for the height. So that means when I plug this into the formula, without the square root? Yes. Why? Yeah, that way you're solving it as an equation and you don't have to worry about a square root. Good. So we'll use, instead of using that, we'll do length squared plus width squared plus height squared equals D squared. So what's my length?
3. Oh, wait. No, 8.
8. So 8 squared plus, what's my width? What's my height? H, I don't know. And then what's my D?
18.
All right. What's 8 squared? 12 squared? 18 squared? Who said that? Somebody said that. All right, 324. All right, now what do we do? You can add or subtract. So you can add these together first and then subtract, or subtract both. So I'm going to add them together, which gives us... Now what? Now subtract 208. 24 minus 8 is 116. And then h squared equals 116. How do you finish that? Square root it. So square root of 116. Is that a perfect square? No. So you can leave it like that. All right? Or you can simplify using your calculator. Okay, go try some. Okay, so we can also use a coordinate plane to do 3-dimensional figures if we add a third dimension to the coordinate plane. So a 3-dimensional coordinate plane adds a third axis, which is called the z-axis. So we have the x, the y, and the z-axis because we now have 3 dimensions to graph. We call the vertices ordered triples as opposed to ordered pairs. So before we had ordered pairs where it was just x and y, now we have x, y, and z. So to graph the point 3, 2, 4, we start at 0, 0, 0. So the origin is still 0, 0, 0. Note, though, that the x and the y-axis are right here, and the z-axis is the one where that would typically be where the y-axis is. The x-axis is typically, the y-axis is where the x usually is, and the x-axis goes through here. So this is a 3-dimensional axis to allow us to plot 3-dimensional figures onto a coordinate plane. So we graph this point 3, 2, 4. We start at 0, 0, 0. We move 3 units forward on x. So 3 units forward on the x-axis would be this way because it's coming towards us. So 1, 2, 3. Then we move 2 units right on the y-axis, 1, 2, along the blue. And then we move 4 units up on z. So 1, 2, 3, 4. So our point would go right here.
So when you're looking for the x, you're going to go down?
Yeah, because it's supposed to be, and it's hard to draw this on like a 2-dimensional figure, but picture the z-axis as like coming out at you. All right? So this is like going back off into the distance. This is coming out at you.
How do you know when you're supposed to use it on this side? Isn't that the negative side?
If this would be the negative side, because it's going back. All right? But then this would be the negative side here, and this would be the negative side here.
Wait, why can't they just like tell you it's 2, 4? Like why it's like go 3?
It is 3, 2, 4. But then this is just giving you the directions for how to get there. So 3 is on the x-axis, then you go 2 on the y-axis, and then 4 on the z-axis. Which is what you do when you plot a point anyway. Like if you plotted a coordinate point and I gave you like 5, -3, you would go over 5 and then down 3. That's what you do. You just do that in your head. Here it's just telling you what you're doing in your head. So I'm going 3 this way on the x-axis, then I'm going 2 on the y, and then up 4 on the z-axis. You do all that work, but you've just been doing coordinate planes for so long with 2 that you don't like draw these lines when you do it.
Why do you go like down and then all the way up?
Because you're not really going down, you're coming out. Like again, we're adding a third dimension, so this looks diagonal because you can't really draw it another way in a 2-dimensional plane. But again, picture that x-axis as coming out of the page at you. Okay, so it's not really, it looks like it's going down. I see that. I know it's hard to visualize. Again, this is why I don't do like nets, because I think it's really hard to visualize. So I don't want you to focus too much on like the actual plotting of them. I want you to focus on using the distance formula with them, which is what we're going to talk about in a second. Okay, but before we do that, if I have a cylinder with a radius of 3 units and a height of 5 units, and one base is centered at 0, 0, 0, how would I draw this on a 3-dimensional coordinate plane? So what do we know about a cylinder? There's no faces, there's no edges. Okay, good. What does it have?
Base.
2 bases, and they're what shape? Circles. So my base is a circle, and the radius of it is how long? 3. Okay, so this circle is centered where? 0, 0, 0. So it's centered right here. And then if the radius is 3, where would I go to draw my radius?
Down.
3 here, and then 3 here. So that's my radius for my circle, right? And then how tall is the cylinder? 5. So where would I go 5? Up 5. So 1, 2, 3, 4, 5. All right, so if this is my base, then what do I have to do up here also? That doesn't look at all like a circle. Imagine that it does. Imagine I could draw well and it looked like a circle. How big is this circle on top? It should be the same size, right? So that means the radius would be how much? 3. So I'm going to go 1, 2, 3 out from here. So 1, 2, 3. And then I would have to go how many this way? 1, 2, 3. Well, I guess these can be straight lines. Okay, so here are the bases. The radius is how long?
3.
1, 2, 3. So if it's 3 this way, how many this way is it?
3.
Okay, so there's your diameter, which would be how much? 6. So there's your base on the bottom. Then how tall is the cylinder? So you had to go up 5. 1, 2, 3, 4, 5. So here's the other base on top. The radius is still 3. So we went 1, 2, 3, and then 1, 2, 3 this way. And there's your radius on top. Or I'm sorry, your diameter on top. Again, don't worry too much about this. Okay, the whole point of doing this is we can find missing pieces using the distance formula. So the distance formula and the midpoint formula in 3 dimensions is exactly the same as in 2 dimensions. It just adds one more piece. So remember the distance formula, the square root of x squared, or x2 minus x1 squared plus y2 minus y1 squared. All that happens in the 3-dimensional plane is, what does it add? Z what? Z2 minus Z1 squared. So it adds the same thing, but with the Z. And the same thing with the midpoint. You add them together and divide by 2, add together, divide by 2, add together, divide by 2. The only difference is now you have to do it 3 times instead of just 2. Because it's an ordered triple, not an ordered pair. So you have 3 coordinate places. Okay? So if I were to ask you, how could you find the diagonal of this? You could use this ordered triple and this ordered triple to find the distance. Or if I said, what is M, the midpoint, you could use the midpoint formula for these ordered triples to find that midpoint. Okay, so in letter A, calculate the midpoint and the distance of the given point. So at your boards, I just want you to do this. Don't worry about practice A here. Just do this A. Okay? So find the midpoint and the distance formula for that A. Go.